Cynthia with the logistics and bringing me here. So I know this is not a topic that normally is spoken much about in this seminar, so I hope to give a general overview of what's going on in the field of small exoplanets, how they get discovered, how do we study them. And I know some people told me that you were interested in knowing what has been going on with James Webb in the last years in the topic of exoplanets. So I have also some slides showing you some general results and some of the latest results from the first year of operations of James Webb in this field. So I'll start with a general introduction on the topic. And here there is a simulation. Let me see if it starts. Yeah. So here you can see the year of discovery and the number of exoplanets that has been discovered in each year. You see the field is very young. It's only about 30 years. But the pace of discoveries have been increasing linearly in those first years. You see that most of the dots are red. Red indicate this technique, the radial velocity technique, for which you use high-resolution spectrographs on typically ground-based telescopes. You see how the discoveries started to augment the pace, and there are more and more of these blue dots. These blue dots are discoveries with the transit technique in which we are detecting eclipses. And you see how this part of the sky gets populated massively around 2014. These are discoveries that came in a batch due to the Kepler telescope. You also see here at the center of the Milky Way some discoveries related to the microlensing technique. And you see how the pace has been increasing until we have reached over 5,000 discoveries a few years ago. We can see here the ecliptic. It's dominated by these transit discoveries too because of the Kepler mission failed in one of its gyroscopes. So the pointing precision got so bad that we needed to change the modus of operations. And instead of staring at that field that we were seeing here, you see that it started to move across the sky, enabling results from different parts of the sky. So this is what has been happening in the last 30 years in exoplanets. We have discovered more than 5,000. We are approaching 6,000 right now. But most of the discoveries that we have get to know, they really are beyond of our imagination. If all exoplanet systems were like the solar system planets, we would have failed miserably. So here you can see a diagram in which you can see the orbital period. So you see here Earth at 365 days, the planets on the solar system as a function of mass in terms of Earth mass. You see Earth here at 1, and you see at 1 year, right? So I'm going to overplot now the discoveries, those 5,000 exoplanet discoveries in this diagram. As you can see, except for Jupiter analogs, we have really not explored the space that our solar system occupies. So we know a lot about how other systems form in the galaxy, but we have failed yet to discover if systems like the solar system, if planets like our Earth, planets like our Neptune, they are common in other stars or not. We certainly know that we can identify kind of 3 types of planets in this diagram. We see this big blob here, which are planets as big and as massive as Jupiter, but in orbits that are of a few days. They do a full run over the stars around in 1 or a few days, and these are the ones that we call hot Jupiters. These are planets that are extremely hot. They are very close to their stars. They orbit very rapidly around it in a very close orbit, and they have their atmospheres completely inflated. They are very easy to detect because they are big and they are near their star. And if you can see that, they are very likely to transit. They are very likely to eclipse the star that we are looking at with our telescope from the ground, because these planets are big, they occupy a big part relatively to the disk of the star, and because they are so close to it, it is often that they pass in front of it. So that's why we have a domination of blue points in these discoveries. from the transit technique. Then we have a mixture of planets that are with a mass between the mass of Earth and somehow the mass of Neptune. There is kind of like a less occurrence of these planets in between that we call super-Neptunes or sub-Jupiters. There are less of them. There are a lot of hot Jupiters, and there are a lot of planets in between Earth mass and Neptune mass. These ones we call super-Earths normally, or sub-Neptunes, depending on their properties. And we see here that they can span a large range of orbital periods, from a few hours till some more close to the 1 year. We see here kind of like a line that separates these discoveries. This is a detection limit. We cannot push into this direction because we do not have the sensitivity to achieve those discoveries, mostly with this technique, the radial velocity technique, which is the orange points. Radial velocity technique is very sensitive to either very massive planets at long distances, for which you need to observe this star for a long time. And as you see in the first diagram, since the 90s, we have these instruments that can be observed. So we have a baseline of 30 years to do this type of discoveries. But we are only sensitive to the most massive planets in that, at those distances. If we go closer to the star, we are sensitive to less massive planets. But they create the same type of signal. That's why we have this diagonal here separating what we can go. If you want to go into this direction, we need to have a precision that is better at an instrumental level. Right now, to make these discoveries, this is a typical radial velocity precision of 1 meter per second, which means that you could see a person walking at a light year distance if you are measuring this type of speed. But for these discoveries to happen, like the Earth-like planets, we would need to measure the speed of a snail on the moon. So this is more or less the type of sensitivity that we require to achieve those discoveries. Okay, so my research focuses on this blob of planets here that are in between the Earth and Neptune mass. And they are the most common, but they do not exist in the solar system. So this is why I am very interested on it. This is a plot in which I am plotting just directly what are the discoveries, but I told you that some of these discoveries are easier than others, meaning that even though these planets we have a lot of them, they may not be intrinsically common. They are just easy to detect. While these planets are very difficult to detect, and still we are detecting a lot of them, probably it's because they are really common. So if you make these corrections in which you correct for the sensitivity biases or the detection biases of your technique, you can achieve a diagram like this one. This one is really the number of planets per star, in which you really have a sense of how many planets are per star in average in the galaxy after doing your corrections. These are results that came from the Kepler mission. The Kepler Space Telescope demonstrated that these planets between size of Earth and Neptune, they are the most common in the galaxy. Almost every star has one of those, if they are, even though they are absent in the solar system. And you see that Kepler demonstrated that even though it discovered so many hot Jupiters and so many Jupiter-sized planets, they are intrinsically rare. Only 1% of all solar-type stars typically have a Jupiter-like planet. If it is a hot Jupiter, it's a 1% of that population. Okay, so you see that this distribution shows a bimodal shape, and because Kepler was sensitive to the size of the planets only, because the technique that I use is the transit technique, we distinguish them by size and call them super-Earths to these planets that are on this left part of the gap. We call this the radius gap. And the planets on the right of the gap, we call them sub-Neptunes. You can see, not very original. But because they are, yes?
Is this kind of like a... Is this like helping answer possibly the Fermi paradox issue? Like, if you don't have if big Jupiter planets are uncommon, don't you have more likelihood of constant bombardment of inner planets and less likelihood of life and that kind of thing?
Yeah, it can be it seems to be one of the main reasons, perhaps, for habitability purposes. the presence of a Jupiter in a system, it really governs all the dynamics, and it really governs how much water you can deliver into the inner parts of the system. So there are a lot of factors that get involved into that. The problem is we are not that sensitive. You see from the previous diagram, we are not that sensitive to this type of Jupiters like ours, but certainly in those systems, we are not able to detect yet Earth like ours. So we don't know if systems here, we just have the sensitivity to see the Jupiter, but we do not see the inner rocky planets yet. So once we have different techniques or more sensitivity in our current techniques, we will be able to see the frequency between having a Jupiter and an Earth-like planet in an habitable zone. Yeah. So as I was saying, this radius gap, this is probably the most important discovery from the Kepler mission. It is the fact that these planets that do not exist in the solar system are the most common in the galaxy, and they show this bimodal shape. But because they are not in the solar system, we have no idea what are they made of. So there are two theories, or two options. You could have the super-Earths and the sub-Neptunes to be a single class of planets. So it is exactly the same type of planet, an Earth-like core, an Earth-like planet, that has or do not have an atmosphere. This could be this type of planet, in which this black area represents what Earth would be like, but slightly bigger, and then you have an hydrogen layer that will increase your size by a lot or decrease your size by a lot if you have it or you don't have it. But another theory or another option is that these type of planets are indeed different types. So you would have planets like the super-Earths that were slightly larger than Earth, and they have the same properties, just slightly bigger in mass and in size. But the sub-Neptunes to be a different type of planet that we call water worlds. These planets would have a large water mass fraction. You would need to think something like a comet, but 10 times the mass of the Earth. We do not know exactly how these water worlds look like. It's not certainly these type of models in which you would have a rocky core, something like the Earth, and on top a big amount of water, do not really work, because that water is subject to a lot of irradiation for most of the discoveries that we do. So that water would be in a steam form, creating a really big atmosphere of steam. But something like that probably is more likely, in which the magma in the interior of the planet mixed with the water, and you have like a very small layer of an steam atmosphere, and most of your water, by mass is a lot, is up to 50% perhaps, similar to the comets or the icy bodies in the solar system, but it is trapped in the mantle, so it doesn't change the structure of your planet from the outside that much. The problem with these two options is that they explain the data as well. Here we have atmospheric evolution models are able to reproduce this shape by taking a population of rocky planets and let them be exposed to the radiation from the star. The planets that are closer to it, they will lose all their atmospheres and be mostly the population that is rocky. And the ones as farther as you go, you will start having these planets keeping onto their atmospheres because they do not receive that much irradiation, and they will make this second peak of the distribution. The problem is the water wall explanation, water planets, because they have a lower density, they have a larger size. So they will create automatically this peak just by their internal composition. And why the water wall hypothesis is being pushed, it has been pushed away in the last years because these models work very well, but the people that work on planet formation, they cannot get rid of the water. In a protoplanetary disk, the part that is inside the iceland in the system will be devoid of water, but beyond the iceland there will be a lot of water. And these type of bodies are very easy to form, and they are very easy to migrate in the inner parts of the system. That's why they would naturally have a larger size and be close to where we detect them, creating this peak of the population. What is the problem? Is that this is the information that we have. We have just size for these planets, while density matters, right? So what we need is to combine the best of both techniques that have been dominating the field in the last years, the radial velocity and the transit. With the transit technique, with missions like Kepler, but nowadays CHEOPS from the European Space Agency or TESS from NASA, you can get very precise radius of these planets. But we combine them with telescopes on the ground with the radial velocity technique that can allow us to measure the mass. And if we have both quantities, then we can measure the density and get a better feeling of what these planets are made of. TESS has played a major role into enabling this type of science because Kepler has discovered thousands and thousands of planets. It had an exquisite radius precision, but most of the discoveries that they did was of very faint stars. Because the telescope was big, most of the discoveries were coming from the very faint stars. Those stars are too faint for being monitoring with typically 3-4 meter class telescopes. But TESS has enabled a lot of discoveries around very bright stars because its strategy is not to stare at a field for 4 years like Kepler did, but stare at 1 month each part of the sky and do a survey all over the sky with cameras that are much smaller, bigger field of view, but the discoveries that it does is around much brighter stars, and those brighter stars are easy to characterize from the ground. So this is what the work that I did during my PhD mostly, and I focus especially on N-dwarf planets. And I did N-dwarf planets because really it was the only type of stars for which we had the sensitivity to really study planets as small as Earth. So if you want to understand the super-Earth and the sub-Neptune population, you may be sensitive. You need to be sensitive at least to the Earth size. You don't want to be cut here just because your instruments aren't precise enough. And for this, we need the help from the star. So this, as a few years ago, these are all the transiting planets that had a measure of their radius and a measure of their mass combining these two techniques. There are about 50 planets here. We did a refinement of their properties with new data, new discoveries, additional data, and refine and measure the properties homogeneously. And if you have a keen eye, you can see kind of like two populations here. And here, I'm just overplotting internal composition models. I'm not doing a fit to these data points. These are just putting a model of the composition on top. So if you take a planet like the Earth and you decrease it in size all the way to 0.5, like half the size, it would have a mass of 0.1 if it has exactly the same composition than the Earth. And if you extend it all the way to a planet 30 times more massive than the Earth, it would have a radius of 2.5 times larger, just because of the composition, right? Like putting 30% iron and the rest on rocks, you get this type of green line. And if you do that and take this Earth-like composition and kind of halve it and add 50% of water on top of it, just keep the rock and add water, you don't care much about how it is structured, if the water is inside, outside, just in terms of bulk density. You can find a line that will pass over all this population. That is explained directly by just having this homogeneous density. All these planets have a very, very similar density. All these ones more like an Earth-like density, and this more like a comet density. If you go all the way here, you would have Enceladus, for example. Enceladus would fit this line perfectly. So this was a big revelation at the time, finding that all these planets have such a similar bulk densities. Because if you expect planets to have hydrogen atmospheres on top of rocky cores, just small changes in their temperature, small changes in the history of the star would have that atmosphere to be exposed to more or less radiation, more heat or less heat, and then change significantly in the size of the planet. Because hydrogen is very sensitive. The amount of hydrogen that you have will provoke big changes in the size of the planet. So finding these remarkable uniform densities must be something more related to have a bulk composition which is very robust to those changes in size. You can see it in a different way. You can create still the radius gap if you put the distribution of the discoveries as a function of radius. You can still create this radius gap, but the gap doesn't tell you what is the composition of the planet, because there are rocky planets that fall in that part, and there are water-rich planets that fall in that size. While if you normalize by the density, you would have very clear and separate populations. You would have a population of planets like the Earth. Then you would have a very strong and narrow peak of these planets that have water content, and then these planets are too puffy for only having water. They require hydrogen atmosphere. These are the planets that are here. In order to match with an internal composition model what is their density, you need to add necessarily a big amount of hydrogen. So this data really agree very well with the predictions from planet formation models. Here you can have a simulation in which you create planets from a protoplanetary disk, and if you create planets all over the protoplanetary disk, the ones that are more close to the star will not have water because the water is evaporated in the pebbles or in the planetesimals, but beyond the ice line, more or less where Jupiter is in our solar system, you will be able to keep the water in ice form. If you leave the system evolve, form the planets, and then let them migrate towards the central star, you would get a distribution of planets that really match very well the populations. While these planets that are overlapping with these discoveries would have a 50% water mass fraction in them, meaning that they form beyond the ice line. You can create this with different planet formation models. You can do it with planetesimal accretion in this case, or pebble accretion. These are different type of cases. When we publish these results, the community that do atmospheric evolution models that they think that sub-Neptunes and super-Earths are the same planet with or without atmospheres, they came up with new models trying to explain the new data. And they found out that if you add a boil-off phase, this is a strange somehow concept in which you have the planets submerged in the disk, in the protoplanetary disk, and there is a lot of gas. So the planets, when they form, they have a lot of hydrogen on top because there is gas. So whatever it is close to their gravitational influence will be accreted onto them. The problem is when the star fully forms, it will blow away the disk. And blowing away the disk, you will have a pressure imbalance in which nothing can keep your big hydrogen atmosphere that you accreted, nothing is in balance with it, and you lose it with the planet. Right? That is a boil-off in which instantly you lose most of your hydrogen that you collected while you were forming. And then the rest of the hydrogen that you accrete, you will be accreting it very slowly with the leftovers that are in the disk. If you do the planet formation in that way, then you will be able to create planets without the atmospheres that fit very well this Earth-like composition. And then you will have a tiny amount of hydrogen that you acquire with time, and that will be proportional to the mass of the planet. The more massive you are, the more hydrogen you'll be able to accrete, and then your size will follow the same kind of distribution that you would have here. So from planet radius and planet mass measurements alone, it seems like it is not enough. So this has been a very, very active debate in the last year. In the last 2-3 years, probably this is one of the hottest topics in exoplanets, is to discover the nature of the sub-Neptunes, if they are water worlds or if they are gas dwarfs. They call them gas dwarfs because it's thinking like a gas giant, like Jupiter, which is thought to have a rocky core and then a big hydrogen envelope on top, right? So we call them gas dwarfs because we are not very good at names, as I said before. So in the last 2 years, there have been a lot of advances. I can tell you some of the results on the latest results just very briefly. This can get very technical. But there has been improvements on the planet formation models. Why is that? Because one of the main criticisms to our first work about the water world hypothesis is that these water world first models that were introduced, they were assuming that water was in condensed form. We know these planets are too hot. I told you at the beginning of in the first slide, you see most of the discoveries have orbital periods of like 10 days or shorter. These planets are too hot in order to have water in condensed form, especially if they are on the outside, right? Like in the outside of in the outer layer. So these people, Remo Bern in Germany, they have been introducing a new equation of state for water in which you take into account that this water is going to be exposed to high temperatures and high pressures and is likely not to be in condensed form, but in supercritical form, creating an atmosphere mostly dominated of water vapor. And if you do that, you would create this nominal case in which these planets are, in which you just find that the planet, this is the gray, is the data from the Kepler mission that I showed you at the beginning. And the new model is able to reproduce with the water worlds, assuming that this water actually is not in condensed form, but creating a water atmosphere, it reproduces exactly the location and the height of the peak very well. While if you assume condensed water, the gap gets blurred because these planets are not that bigger compared to the rocky cores. And if you don't put any evaporation at all, if you don't let the star work on that atmosphere and remove part of it, then you do not create at all the super Earths. So it is both a combination of evolution processes, like the photoevaporation, and it is also from formation principles, having this amount of water from the beginning that comes from formation and migration. There are also a lot of new discoveries of individual planets that has been proposed as water world candidates, that they fall into this line and they cannot be explained by having a hydrogen atmosphere despite their size, just because they are too hot and that atmosphere would have been blown away, or because there have been atmospheric detections in which there have been measured water. So there have been new discoveries of this type of planets. Most of the discoveries have been done around M dwarfs. So it seems perhaps that M dwarfs are more favorable to have these water worlds than the sun-like stars. So is this enough? Because with the data that I show you, you can explain with both theories these planets being either a gas dwarf or a water world. You can choose the theory that it is more convenient to you, but you will not get a robust answer. So the hope is now to use James Webb. So mass and radius measurement seems to be insufficient, at least at the way that we do them now, to distinguish what is their nature. There are too many options. You can have many combinations of iron, rock, water, hydrogen to match the density of those planets. It is the degenerate problem. So the thing is, with atmospheric characterization, you could see the interior by checking the atmosphere. And there are some mechanisms proposed that, for example, if you have a massive hydrogen atmosphere on top of a rocky core, this is the gas dwarf scenario, you would have different molecules in the atmosphere with respect to a planet that has a smaller hydrogen atmosphere, but it is on top of liquid water. For this, you need water to be in liquid form. So not all planets are hot enough or cold enough to have water in liquid form. But if you have heard about K218 in the last months, this is one of the cases in which it could have a liquid water ocean, and on top it has an atmosphere. And the atmospheric detections, the atmospheric spectra will look different. It will have different amounts of methane and carbon dioxide, and some of the planet would have ammonia, and others do not. So there is some disequilibrium chemistry at place, because there would be a liquid water that would act as a sink of some molecules, that you could use the atmospheric observations, which is of this part, to check what is the interior, if the planets have a lot of water or do not. But can we do these observations with James Webb? Is James Webb good enough? This is what I'm going to show you, some quick results from the latest years from the last year and a half of James Webb. So don't know if you saw the launch on Christmas Day in 2021. I certainly did. The operations started in June 2022. So it's been a year and a half. We are closing into 2 years now of data, getting data from James Webb regularly. And the launch was so successful that really the original 10-year mission, now it can be over 20. So the launch was so efficient that the lifespan and the life expectancy of James Webb has doubled or tripled. So there is a lot of science that is going to come from this telescope. So this is just an overview of some of the latest results, the most important results in the last year and a half from James Webb. One of the important discoveries have been done for mostly hot Jupiters, because they are the easiest to detect. And there seemed to be a lot of carbon dioxide. This was a molecule that was never being observed and detected before. It was supposed to be there for most of these planets, but it hasn't been detected before until James Webb came. We found for planets that apparently in their properties should be very similar, they have very diverse atmospheric compositions. We see the effect of non-equilibrium chemistry directly on planets because of the detection of some of the molecules that we are doing. we have been doing some maps, like kind of 3D maps of planets, in which you can measure if there is weather on them, if there are winds, if there are different parts of the night side, and is it colder than or hotter than the day side of the planet. You can have some 3D views of planets nowadays. And also we have studied some terrestrial exoplanets that are likely rocks. So these are some of the results. This is the CO2. I think this was the first ever CO2 was seen, and this was the picture proving it. So you see it's a picture of on a screen, really, really with the first data that came from James Webb. And this massive feature, this is 4 microns, really nothing was able to go to 4 microns. Most of the Hubble results are centered around 1.4 microns. So something here, and you see the data is not even good for James Webb in this area, right? So really you see this big feature here that is related to CO2, and the beautiful version that was published in the first paper in Nature, it is this beautiful bump. This CO2 was done for a hot Jupiter, was 39b, but it has been really measured for many other planets, and we are starting to see some trends. Some trends with the mass of a planet as a function of metallicity. Atmospheric metallicity, like astronomer metallicity, mostly is just carbon to oxygen ratios, because these are the molecules that we mostly being able to detect. So we're really measuring the amount of carbon relative to oxygen for these exoplanets. But now we can see some trends that in the solar system may hold for Jupiters or gas giants that are hot also in the rest of the galaxy. Also, I told you there is non-equilibrium chemistry. There is direct evidence of photochemistry in which just photodissociation of water leads to this process in which hydrogen sulfide, which is very common, it's a very common molecule in these gas giants, will become sulfur dioxide. And it's this small bump here. So this SO2 you can really form if there is photochemistry acting on. Here is the full reaction. And this detection has been subject to a lot of recent articles, both in the modeling, but also in the actual analysis, because detecting this is, you just need to see how these wiggles are significant or not significant. So this has been also one of the latest results. And for the smaller planets, we now can measure the temperature of these rocky planets. The TRAPPIST-1 system is one of the most studied with James Webb during the first year. And TRAPPIST-1b, it is the closest to the star, the hottest planet. And you can study the planet. Instead of wait for the planet to pass in front of the star and see the atmosphere through, you can wait until the planet is behind of the star. So you are measured the difference between the starlight and your planet day side when it is in this limb. Then when it's passing behind your star, you are getting an absolute value of the brightness of the star without being contaminated by the planet. And then when it comes again, you can check what is the starlight plus the day side. So it is a way of measuring what is the contribution. This jump in flux, it's related in a jump in temperature, and that can be related. You can measure the temperature of a rocky planet, which will be different if you have an atmosphere or not have an atmosphere. Instead of directly measuring the atmosphere, you will see if the planet is colder or hotter than expected if it has an atmosphere. So the result, here you would have, this is a TRAPPIST-1 model in which you would have an atmosphere. That atmosphere will distribute heat evenly around the planet, so it will make the planet in average colder, right? It would be something around 400 K. But if you have a planet that has a completely dark surface with no atmosphere, there is no redistribution of heat, so you will have the same temperature than a pure black body would have at that distance from the star. This is the model, and this is exactly what it was measured for TRAPPIST-1b. So really, really, really close to being just a rock. Space rock, very hot, no atmosphere. Does this tell us that all rocky planets will not have atmospheres? We don't know. This planet is certainly too hot to perhaps have being able to maintain an atmosphere. And TRAPPIST-1, for those of you that know, this is a very, very late M dwarf that has a really strong magnetic field and stellar activity, and it's just not the best environment for keeping an atmosphere alive. So these are the results, a little overview from different results from James Webb. But what about the sub-Neptunes? That is the ones that we are talking about today. So there has been only 3 observations of sub-Neptunes. There is GJ1214b, K218b, and TOI270d, and all have had detections of water, all of them. But these are planets that are slightly bigger. You remember the planets that I told you were puffier, they were too puffy to not being just purely water. They need some hydrogen. These are these type of planets. They may have a water component, but they certainly have a hydrogen atmosphere. That's why you have these signals are bigger. This is K218b, and this is the first time that methane was detected in an exoplanet. The methane problem has been something that has preoccupied the field in the 10 years because methane, it was a species that was supposed to be easily found and wasn't found at all in the last 10 years using James Webb, using Hubble, using ground-based telescopes. But now with James Webb, there are now no doubts. These are several bumps, several detections of methane at different wavelengths. There is a CO2 and a big CO2 feature here. And there is this DMS. I don't know if you have heard this, but this stirred the community for a while a few months ago. This is dimethyl sulfide. This is something that on Earth exists because of the interaction of plankton. So this is a biomarker. And this is a tentative detection of DMS. So the media took this as there is life on other planets. The authors, they didn't, but they certainly publish it. And they try to eliminate this signal, right? And that's why they call it tentative detection, because this signal is now barely 2 sigma and a half or something detection. But if you apply some offsets between this instrument and this instrument, you can kind of get rid of that signal. So this dimethyl sulfide, right now, it is a topic of active research, I would say, on the newspapers, but not on the scientific community. But the methane and the CO2 and not finding water for this planet, it is the thing that is preoccupying the most the community. The methane suggests that there could be a liquid water ocean under the hydrogen atmosphere. But this discussion is the one that the authors present in the first paper, but has been very discussed. And you can have a model in which you have a lifeless Haitian, in which you have a rocky planet with water, but not necessarily a liquid water ocean. This is not a good fit. You see, this is not a good fit. But these 2 fits are equally good. And this would be a planet that has a liquid water ocean, then the hydrogen on top, or this is hydrogen on top of the rocky core. So this is a gas dwarf, and this is a water dwarf. And they both fit equally good the data. You just need to make the model properly. So these are some of the things that are being discussed right now. Are there other features that could clarify this? Yes, there are features at 9 micron that with MIDI maybe be able to confirm different features of sulfides and shallower water bands in the mid-infrared. But this is something that is being discussed really a lot, because it seems that we may hit the same problem that we were doing with the mass and radius measurements, that now both scenarios can also explain the atmospheric data, right? So we need to make sure that our models and our precision and our understanding of the instrumental systematics for James Webb also are at the top of our level. So what is the present and the future, I would say, for this science case? So if atmospheric characterization is really the only way to go forward, because if we want to give a statement that is based on observations, this is the only thing we can really do, especially now. So we have James Webb is opening a new part of the parameter space. Before we could do only atmosphere for hot Jupiters, now we can do them for sub-Neptunes. That's completely new. So that is the first step, and it's combining with the measurements that we have been already acquiring from masses and radius. But the interpretation of this spectra the atmospheric observation is going to be challenging. It's going to be very difficult to distinguish between a flat line when you have atmospheric data from the James Webb, and it is a flat line here, completely flat. That could be evidence of no atmosphere, right? But then you could have an atmosphere that is very heavy. An atmosphere with a very high mean molecular weight would have features, but they will be so shrunk that they will be look like a flat line. But if you have clouds, even an atmosphere that is huge, you have a high cloud deck. Those clouds will remove any information of the spectral absorption that you have, the molecules that you have. So a cloud, a high mean molecular weight atmosphere, meaning a dense, heavy, metal-rich, like water vapor type of atmosphere, or no atmosphere at all look the same in transmission. So first of all, you will need masses because you need masses to put your retrievals in the models. And you could do emission in which you are looking directly, instead of through the side of the planet, it's a slant optical path, you could look directly on the mission, the same that it was done for TRAPPIST-1b. Just wait for the planet to pass behind the star and look at the planet directly, the day side, and measure the temperature. But for this technique really apply only to the planets that are very hot, because they are so hot that they emit enough in the mid-infrared for you to detect it. But the colder ones, it's like the Earth, right? Like you need to go to the far infrared or almost radio to detect the actual emission from Earth. So these are the difficulties that comes with this topic. But there is an ideal target, an ideal system. This is a recent discovery that we published, I think it was November, and it is HD 110067. So these are 6 sub-Neptunes. They are all transiting. They are orbiting a very bright star. It's a nearby star, like 100 light years, magnitude 8 or something. You could see with a binocular. And they are in a resonant chain. What means this resonant chain is that their orbits are synchronized. They are trapped in first order mean motion resonant ratios. So the period of the planet, this planet compared to this one, is an integer. So these are 3 orbits when this planet does 2 orbits. Then this one also is in a 3 to 2. This planet does 3 orbits while this one does 2. Then this is 3 to 2, 3 to 2, 3 to 2, 4 to 3, and 4 to 3. These 6 planets are trapped in this resonant configuration, which can only be created at formation. So we know the system hasn't changed in the billion-year history of the system. There has been no dynamical changes on the configuration. You can only get trapped into this configuration while there is a disk, because you are doing convergent migration and all the planets get trapped in these stable configurations. Then the disk blows away and the system remains the same. Is this common? Not at all. Because most of the multiplanetary systems that we discovered, they are not in this resonant configuration. The solar system is not in this configuration, but the Galilean moons in Jupiter are. So these are relics of planet migration. So you have a very bright star, so you can do a lot of observations with it. You have 6 planets that they span a range in temperatures and radius and masses that allows you to do comparisons. And then you have this primal resonant configuration that allows you to trace back the orbits to where they were formed, knowing that there hasn't been anything that disturbed them. So it is a really unique system for planet formation, dynamics, compare planet properties between them, knowing that the star is the same for all of them, so their history is common. And then it is really bright that all these planets are ideal candidates for James Webb. There is nothing remotely close to their observability properties. So these are my final thoughts on sub-Neptune science. And one of the first is that there are not many candidates that you can really do all these studies. So first, you need a transiting planet. For a transiting planet, you need a unique configuration in which your telescope, the star, and the planet are all aligned. So you are reducing your chances of a discovery by 1 in 1,000, just because of, even though there may be planets in all the stars, not all of them are transiting from your point of view. So you are cutting a lot of discoveries from there. Then you need the star to be bright enough for measuring the mass with your ground-based telescope, which is normally 3 meters or 8 meters big. And then you need the planet to have an atmosphere, and then you need the star to be bright enough, and the properties good enough for doing atmospheric science with James Webb, which is not good for all targets. Targets that are very far away, planets that are stars that are too dim, they may not be good. So there may be a few hundred planets that really, realistically, we can do this type of studies, measure their mass, their radius, their atmosphere. So we really need to make the most of them. And to understand what are these planets made of, what is their nature, we really need to put everything together, because their amount of water comes from planet formation models, how this water is distributed, what is the internal composition, is the water trapped in the magma, is the water outside, how it connects with the atmosphere. All those things are going to impact your models that you are going to compare your data with. Also, planet evolution is important, how really atmospheric escape works for an hydrogen atmosphere, but also for a water-rich atmosphere, for a steam atmosphere. We need to be better at our systematics in James Webb to improve our actual atmospheric characterization, the collection of the data, the interpretation, the modeling, the impact of clouds and hazes. And also, this has consequences for astrobiology. If these planets really do have those amounts of water, what are their conditions in which they could be habitable? It's the same that we are trying to explore Europa. We are trying to explore Enceladus. There may be different ways in which these planets could be in a parameter space different than the one needed for Earth for them to be habitable. And all these processes really affect each other, so they cannot be addressed separately. So I think I have a few minutes to go through the final slide. So just some take-home messages. Sub-Neptunes, most abundant planet type in the galaxy, but not in the solar system. We can only study through indirect methods, right? It's not like Jupiter or Neptune or the moons of Jupiter. We cannot go send a satellite and have direct data. So most theoretical interpretations really for the origin and the nature of these planets really can reproduce the observations. So take your model, they all seem to explain the data very well, because they are intrinsically living in a part of the parameter space that is degenerate. The gas dwarf hypothesis has been historically the one that had the most traction in the field, but in the last 4 or 5 years, really there is a lot of evidence that water walls, at least for the endors, for the smaller stars, they cannot be ignored. There seem to be really a population with different properties than the others. And then we need measurements of their mass, their radius, and their atmospheric composition just to get started, right? So the future is to do demographic studies in which we are putting these properties, measure for all of them in the context of the stellar mass, metallicity of the star, the temperature of the planet, and other properties. And those are the only way in which these theories really start making different predictions. It is how these planets, what is their frequency, going from endors to sun-like stars, going from close distances to long distances. These are the only things in which the theories really start to diverge. And the candidates are just a few hundred. They are very precious. And it will really it will require an improvement of our understanding in many fronts, especially in the theoretical side and also laboratory work. There is a lot of laboratory work that can be done, especially for understanding the effect of planet formation, how planetesimals collide, stick together, dust, measurements of clouds and hazes particles with different gas backgrounds. All those works are done in the lab, and they are very important too. So be happy to take any questions, and thank you very much for listening.
So I have 2 questions. First, did the Webb proposal get through?
For the previous system?
The resonant chain?
No, it didn't. It didn't get through.
A pity.
Yeah. Well, second time we tried.
Second question is, you talked about clouds and hazes, and I was curious, as a non-expert, I would have thought that maybe albedo is something that could tell us about clouds. Is that useful or still too degenerate?
Yeah, Albedo is really the property that we measure directly in emission. So we either measure a zero albedo and then we think there is no atmosphere, or we measure a high albedo and then we think atmosphere. But our direct measurement is of albedo. Albedo is degenerate with the composition of clouds. So if you have clouds like the ones in Venus, then you would have very high albedos. But if you take other hazes like soot, you would have very dark albedo. And this will not tell you anything. Both planets have an atmosphere. It's just because their composition is different, they will show different albedos. But if you don't know anything about the composition of those hazes, for the bright albedo, you would think that this planet has an atmosphere. And for the dark albedo one, you would think this planet do not have an atmosphere, not that has an atmosphere with a dark haze. So yeah, it is totally degenerate. And that's why laboratory work is important, because a planet that do not have an atmosphere shouldn't have any spectral feature. But hazes, because they are made of elements, they will have spectral features. It's important to identify in which wavelength ranges and what is the sensitivity, and if we should explore to see features. And instead of seeing features of the atmosphere composition, we would see the features of the gas, of the cloud or the haze. And this is something that is work in progress right now.
Okay, thank you.